In this skill, we're again using Le Chatelier's principle, which tells us that for a system that's initially at equilibrium, if there's a stress that happens, the equilibrium position will shift to counter that stress. So in this particular question, we have a container with fictional substances Rg2, R, and G2, which is initially at equilibrium. That's good because that means we can use Le Chatelier's principle. In our equation, we can see we've got 1 mole of Rg2, which is a gas, 1 mole of R, which is a gas, and 1 mole of G2, which is a gas. In this skill, the stress that's going to happen is a change in the volume of the container and therefore a change in the pressure of the gas in the container. So we're just going to be focusing on gases. So our first questions here are asking us how many moles of gas are on the reactant side of the equation and how many moles of gas are on the product side of the equation. So on the reactant side, we've got 1 Rg2. So we've just got 1 mole of gas on the reactant side. On the product side, we've got 1 mole of R and we've got 1 mole of G2. So that's a total of 2 moles of gas on the product side of the equation. We're then told that the system is stressed by increasing the volume of the container, which decreases the pressure inside the container. That makes sense based on our gas laws. We know if we increase the volume, our gas can spread out more, the particles will be further apart, and we're decreasing the pressure inside the container. Okay, so the pressure is decreasing. That is our stress that's happening. So according to Le Chatelier's principle, the change that needs to happen is the opposite. If the pressure is decreasing, we need to increase the pressure to counter that stress. So we're always going to be having the opposite thing to whatever our stress was. So if the pressure decreased, therefore the change that needs to happen is that the pressure needs to increase. Okay, so if we need to increase our pressure, we need to increase the number of moles of gas. So looking back at our equation and looking at our answers to these questions up here, in the reactant side, we have 1 mole of gas. On the product side, we had 2 moles of gas. So if we need to increase the number of moles of gas and therefore increase the pressure, if we make the forwards reaction happen at a greater rate than the backwards reaction, we're going to be producing more moles of gas because the product side has more moles of gas than the reactant side. So if we focus on the forwards reaction having a greater rate, that means we're going to be producing more moles of gas, which means we're going to have a greater pressure. So which reaction direction needs to be favored? It's going to be the forwards reaction because it increases the total moles of gas. Increasing the total moles of gas is going to increase our pressure. So because of that, our equilibrium position is going to shift towards the products to the right. Let's do one more question of this type. In this question, we again have fictional substances. This time it's Re2 and Re3. We're told it's initially at equilibrium, which means we're going to be able to use Le Chatelier's principle. Here's our equation. We've got 2R, which is a liquid, 3E2, which is a gas, and 2Re3, which is aqueous, in other words, a solution. So the first thing we're looking at is the number of moles of gas on the reactant side and the number of moles of gas on the product side. So on the reactant side, we've got 2R, which is a liquid. That's not a gas. So we've got 0 moles of gas coming from R. Plus, we've got 3 sets of E2, which is a gas. So that means we've got 3 moles of gas there. So that's a total of 3 on our reactant side. On the product side, we've got 2 sets of Re3 AQ, aqueous, which means a solution. Again, that's not a gas. So changing the volume of our container isn't going to change the concentration of our solution. So we've got 0 moles of gas on the product side. So it's important to remember here, as I've just shown, the only thing we care about when we're talking about a change in volume of container and a change in pressure is the gases. Anything else isn't going to have any effect. Okay, we're then told the system is stressed by decreasing the volume of the container, which increases the pressure inside the container. So our stress is that we're increasing the pressure. So according to Le Chatelier's principle, we need to do the opposite thing. So we need to decrease the pressure. So what change needs to happen? The pressure needs to decrease. So if our pressure needs to decrease, that means we need to decrease the number of moles of gas. So looking at our equation up here, we said we have 3 moles of gas in the reactants and 0 moles of gas in the products. If we need to decrease the moles of gas, we want the forwards reaction to be happening at a greater rate than the backwards reaction because we have less moles of gas in the products than we do in the reactants. So some of our moles of gas in the reactants will be converted to not a gas. So we're decreasing the amount of gas that we have and therefore we'll be decreasing the pressure. So which reaction direction should be favored? It should be the forwards reaction because it's going to decrease the total moles of gas. In which direction will the equilibrium shift? It's going to shift towards the products to the right. So in these questions, first we're counting up how many moles of gas we have on the reactant and product side of our equation. Then we're looking at the change that happens. Remember, according to Le Chatelier's principle, we want to counter that change. So if the pressure increases, we need to make the pressure decrease. If the pressure decreases, we need to make the pressure increase. Then we're going to choose the direction of the reaction that should be favored in order to make that happen. If we need to increase the pressure, we need to favor the direction that will increase the number of moles of gas. If we need to decrease the pressure, we need to favor the direction that will decrease the number of moles of gas.